Okay, thank you, Thomas. So actually, this work was done by John Hughes together with Scott, John, and Dizzy from Basho. So I've been working with Basho on some other stuff, but this should really be John giving this talk. But fortunately, he couldn't come, so I'm here giving the talk in his stead. Okay, as you all know, all the cool kids these days are working with big data because it's big, right? Well, what do you do when you have big data? Well, it's too big to fit on any single machine, so you have to store it across a whole number of machines. So you distribute it, and then of course you're using Erlang because what else would you use? So distributing it means it's scalable. You just add more computers to your cluster, and then everything just works. The data, you typically replicate the data so that each piece of data is stored on a number of machines, which means you get fault tolerance and low latency. So if one machine goes down, you have the data on some other machines as well. High availability, the same. You can, if you're asking for something, you just get it from the closest machine. So that's where you get the low latency bit. And one system for this is the Riak system, which is what Basho is doing, which has exactly this model. So what you lose, as Thomas mentioned, in this scenario, you get all these nice features, but your query language is much more restricted. So you can't fire off arbitrary SQL queries. And in the Riak case, what you have is just a key value store. But for a lot of purposes, that's actually correct. That's all you need. And if it means you can handle huge amounts of data, then that's fine. Okay, so what's the problem? Well, the problem is we want to test this. We want to check that our Riak database is doing what it's supposed to. So you have to, somehow we need to ensure that it's correct. This is, by the way, this is how John looks like when he's thinking really hard. Okay, so fine. We have to somehow test the Riak implementation to make sure it's correct. Well, the first question is, what does that even mean? What does it mean for a distributed database to be correct, where you can have nodes going up and down at any time? It's not even clear what correctness means in this case. So what do? Well, I'm from QuickCheck, so the answer is, of course, we use QuickCheck or property-based testing, as we've seen a little bit about today. So, but still, we still don't know what correctness means. So a good approach in this case is to start off with the simplest possible model of your database, in this case, that you can think of. In this case, let's just go one key, one value, and a naive model of how the database works. We know that's not going to be a correct model of Riak, but if we start out with that model, we're going to find out where it doesn't match up, and then incrementally we can work towards a more complete specification of what correct should mean in this case. So that's a nice thing with property-based testing, that you can, it not only guides you towards a correct implementation, but it can also guide you towards a correct specification in cases where you're not quite sure what the correct behavior is. Okay, so let's look at an example of how this works. So here's our database, Riak, in the cloud, and these guys are two users interacting with the database. So, for instance, the first user puts 0. So remember, we only have a single key. So when you put a value, you just put, it's just a value, there's no key, there's only one. So the first user puts 0. The second user does a get from the database. Of course, he sees 0. You can then do a put with 1. And then the first user again does a put. And of course, he gets the newly put value 1. So we could write down some unit tests, of course, with various sequences of gets and puts, and then try to figure out what the correct answer should be for each of those. But that's not how we do it with property-based testing, because it's really boring and time-consuming. So what we do instead is we have QuickCheck generate these sequences of gets and puts. So QuickCheck would generate a test case like this with a bunch of gets and puts with some arguments, telling which user is doing the put and what value and so on. And then we have a model of what we think Riak should be doing. And in this case, the model is just a single value, right? The value that was last put into the database. And then we run, or QuickCheck runs this sequence. And then for each command in the test case, you have a corresponding state transition function that modifies the state accordingly. So in this case, the put, when you do a put, you would replace the value in the model by the value you put, and get wouldn't change the state at all. And then at each command, you would check some post condition. For put, there's no post condition. For get, we would check that the value we get from the database is the one that we're expecting, so that it corresponds to what the model says is in the database. So that's our super simple model of Riak, which we're pretty sure is going to be incorrect, but it'll be interesting to see where it breaks down. So let's look at that. And then hopefully that will guide us towards a better specification, an actually working specification. Okay, so here's an example with just a single user. So we do a put with the value 0. We do a put with the value 1. And then another put with 0. And then we do a get. And what should we get here? Yeah, you'd kind of expect 0, right? And that's what the model, our simple model would say 0. But in this case, Riak came back and said, no, 1, which is very surprising just looking at this sequence. But in fact, there's some more stuff going on. So there are two ways you can put a value into Riak. You could either create a new Riak object and put in the database, or you can use an old Riak object that you got from the database and modify it some way and then put it back. So in this case, the first put is a new, well, of course, because we haven't seen any Riak objects, so it has to be a new. The second put, we've updated the object that was returned by the first put. So when you put something, you get the newly created object back, I guess. But then the third put, instead of using the object that we got from the second put, we put a new object in there. So that's a clue to what's going on. So what the Basho guys said when we found this was that, well, you shouldn't do that. You wouldn't. I mean, you've got the old object here. Why would you create a new one? You should use the old object, of course. So this is just silly. And what's the reason for this? Well, the way Riak keeps track of what value is the most recent ones when you have lots of writes from different users, is that there's a vector clock, which is pretty much just a sequence of numbers. And then when we were doing this, the vector clock kept a counter for each user. How many times had that user touched a particular value? So in the first put here, the new one, the value you put in would have been touched 0 times by that user, or 1, I'm not sure. And then we do an update, which would increase the vector clock for that user by 1. So you'd have an object in here which had been touched twice by this user. And then we put a new value, a newly created Riak object, which would have a fresh vector clock. So it would only have been touched once by this user. So when it got to Riak thought, well, this is an older value than the 1, because the 1 has been touched twice, the 0 has only been touched once, so the 0 was discarded, and it kept the 1. So, okay, we shouldn't do that, so fine. It's not a bug. That's just how Riak works. I wonder if the users know that. So anyway, you shouldn't do it, but the question is that clear to everyone? And moreover, is it clear that if you do it, that you could actually lose the data you're putting in? So it might be, the intended behavior, but is it a good behavior? Maybe it's worth thinking, changing it, which in fact the Basher guys did later. But okay, for this, for our model now, what should we do? We found out that the simple model wasn't enough. So what we have to enrich our model in some way to handle this behavior. So one thing you might think is, well, we could put the vector clocks, I guess, into the model and model the behavior of these vector clocks, and then we could capture this, how this works. But that's not what we should do. That would be complicating the model more than necessary. I mean, we don't really care from a user's perspective. We don't care about the vector clocks. That's just an implementation detail that we don't really want to see in the specification. And in this case, it was really a bad test case. You shouldn't do this, right? So why don't we put that into the specification and make sure that we don't generate these bad sequences where we do an update and then a new. So we're enriching the model so that we keep not only what the value is in the database, but also the last view of the value that each client has. So when it does a get, it gets a view of that value, and also when it does a put, I suppose. And then when you do a put, we only allow these update puts unless you don't have a view, you don't have a Riak object, in which case you have to do a new. But if you have one, you have to update that one. And then all the tests that we generate would respect this precondition. So we would never actually generate this bad sequence from before. So that means we can move forward. We're not going to see that particular problem when running tests. So then, the next question is, what happens when you have more than one user? So here, so we've got two guys writing and reading from the database. So what happens if they write at the same time? So this guy writes 0, this guy writes 1. What you get from the database if you read it after these two operations? Well, the way I think you can configure this, but the default behavior is that you just get a list of the possible values back. So you get sort of a conflict. So, you know, we've got multiple writes here, and we don't know which one is more recent. So you get all of them. But then, if you know, this guy does a get, he sees all the conflicting values, and then he does a put. Then, since he's seen the conflict, the put he's doing here will resolve the conflict. He's got all the information here, so when he put the 2 here, we're going to replace the 0 and 1 by the 2. So if the other guy does a get after this put, then he's going to see only the 2. So the way we're going to model that is, instead of just keeping a single value in the state, in the model, we'll keep a list of values or a bag of values, keeping track of all the possible conflicting values that we have at any one time. And then each client has a separate view on what's in the database, which will be also a list of values which can be different from what's actually in the database. And when a client does a put, then you'd replace the values that client has seen would be replaced by the value that he's putting. So to model this conflict resolution, you get something from the database and there's a conflict, then you look at all the values and you reconcile them in some way, and you put back a single value as the new value. So that's what we're going to do. All right, so example. So we get first guy does a put, second guy does a put, first guy does a get. So we've got a conflict, so he's getting 0 and 1. There's a third guy, which does another put with 2. First guy does a put with 3, so he's resolving this conflict between 0 and 1 by putting 3. And then there's a get, again by the first guy. So what would we expect to see here? 2 and 3, yeah. So the first guy resolved this conflict, but the 2 there wasn't in it, so the 2 should still be there, and we should see 2 and 3. Oops. Actually, we didn't. Yeah, so that's interesting. So what this turns out to be is that it's a vector clock optimization. So Riak doesn't keep a vector clock for each value. So 0 and 1 and 2 don't have different vector clocks. So it just keeps one vector clock for the entire object with all the possible conflicts. So when the 2 is put here, it loses the fact that 0 and 1, this put here, updates is newer than the 0 and 1. It just sees at this point it sees 0, 1, 2 in the database, and the 3 is not newer than 0, 1, 2 because the 2 over here has not been seen by this guy. So it'll just when the 3 is put, it'll just become a bigger conflict between 0, 1, 2, and 3. Okay, so again, this isn't a bug in Riak. This is just how it works. It's just that we didn't fully understand what the behavior was when writing the specification, the model, intentionally, right? writing the model partly to understand what the correct behavior should be. So how should we model this in a better way? So what we had before, we had the state of the database was a list of values, and then each client had its own view of what values were in the database. And then when we did a put, we did this conflict resolution, replacing the client's view by the newly put value. But in fact, this turned out to not be what really happened. So it didn't really replace those particular values in the client's view, as we saw in the previous example. So what we can do is just change the models to, instead of keeping track of the list of all the values that a client think is in the database, we just need to keep a bit saying, is the client's view fresh or stale? So in this case, when the first guy here does a get, he sees 0 and 1, his view is fresh. It's just done a get from the database. But as soon as the third guy here puts the 2, then the first guy's view becomes stale. Now, the database has 0, 1, 2. The first guy thinks it's only 0 and 1. And then when you do a put, if you have a fresh view, then you replace the state of the database. But if you have a stale view, you just add whatever value you put to the list of conflicting values. But so far, we've really only we haven't really done any interesting distributed stuff, right? This was supposed to be about eventual consistency, and really the Riak cloud here is just a single node. You haven't really done anything about this distributed, fault-tolerant, replicated stuff. So let's look at that next. So how does that work? Well, the way it works is that you store, by default, I think, each key value pair on 3 different nodes. So when a client does a put, then that would be written to 3 separate locations, so that if one of them goes down, you still have the value around. You don't lose anything. So if you do a put with 0, and then the third node here goes down, what happens when you do another put and the node is done? Well, then in that case, well, it's writing to the first 2 because they're up, but then this guy is down, so it's writing the value to a backup node. So every key has a sort of list of all the possible backup nodes in order. So if this one would be down, there's yet another one where it would store the value. And then this guy, the fourth, the backup node, remembers that it's not really supposed to have this key. It's just holding it for the third guy. So when the third guy comes up again, when it's rebooted, there'll be a handoff. So the backup node will notice that the third node is back up, and then it'll send over the key and value to that node, and that's called a handoff. Okay, so how should we test this? Well, you don't want to go out and find a huge cluster of machines and start taking them down at random points in time, because that's not really going to work. So I think what you were doing was you pulling out the logic that we're doing this and testing that logic in isolation. And then, so we generate a sequence, puts and gets as before, But instead of just having one node and always writing to that, these would write the values to an arbitrary or to arbitrary fallback nodes. So instead of actually taking down nodes, we're just simulating nodes being down by putting values on different nodes. So that's the test case. But then what do we want to, we want to test eventual consistency. So eventually things should become consistent. When does eventually happens? Well, one way of doing that is to say, well, first we run our operations, and then we just run as many handoffs as are available. So after we've run this, we pretend that all the nodes are up and let them do all the handoffs that they want. And after they've done that, we expect to see a consistent state. So if we do a get after all these handoffs, we should really get something consistent. Okay, so that's what the test cases are going to look like. But what's the correct, what does this mean to be a consistent state down here? So here's John thinking not quite as hard. Should we model the locations? I mean, we could keep track of every time we do a put, which nodes were up, whether we're written, and then model exactly what the handoffs are doing to keep track of what we expect to see in the database in the end. And maybe you can guess that the answer to this question is, again, no. So that's also going into too much detail, too much implementation-specific detail for the problem at hand. So what we chose to do instead is to say, well, when we do the final get, then we might see a value if it was put at some point. If it's been put at all, then it could conceivably end up in the final get. But it must appear in the final get if it was put and never replaced. So if we don't have anyone with a fresh view resolving a conflict involving this value, then it should still be there. So that's easy to put in our property, and then we can run it. So here's an example. So we do a put of 0. We do a get. That should get 0. Another get. And a put, so this replaces now the 0. And then we do a put. And in this case, we expect to see 1 and 2. We might also see 0. That's, I mean, if we did, it wouldn't be an error. But we should definitely see 0 or see 1 and 2 because they've been put and no one's replaced them. So what do we get? Well, here's what's actually happening. We do the put, but then these two nodes are down. So it's only put to the top node. And then when we do the get, the top node is down and the other two are up. So this guy gets not found instead of 0. And then in the rest, all other nodes are up. So you do a get, it gets 0, it puts 1, this one puts 2. And then we do the get in the end, and then we only see 1. Huh. That's weird. So remember the very first failing test we had, where we were doing a put new and then an open and then a new again, and you weren't supposed to do that. Well, this is exactly what's going on here. So the first put up there is obviously a new one, but then we were expecting this put to be an update. But in fact, since the second, the get operation, return not found, we don't have an object to update, so this put would be a put new instead of a put update. And then the clock magic will just discard this, because this put here will create an object which have been touched once by the first guy, putting 0, and once by the second guy, putting 1, and this object that comes in here has been touched once by the first guy and never by the second guy. So it's strictly older than the object that's already in there, so it's going to be lost. So this is the first bug, which wasn't actually a bug, it was just working as intended, that comes back when we start looking at distribution and nodes going up and down, and this handoff business. So now, there's an actual bug in Riak. So Riak isn't eventually consistent. Well, it wasn't eventually consistent. It is now, because once we found this, of course, the Basho guys quickly fixed the problem. And the fix, as I think I mentioned, was instead of using a vector clock that tracks how many times each user has touched a particular key, it tracks for each node. It keeps a vector clock, or an entry in the vector clock for each node, which means that this particular bug goes away. Okay, so what were we doing here? We were using QuickCheck, which let us start off with a super simple specification, which we knew it was wrong, but it was very helpful as a starting point to start with a simple specification, because we didn't really know what the right specification should be. And I think if we'd started trying to write the correct model from the beginning, we wouldn't have thought of this fresh and stale view business. So it's a very helpful technique to just start out with a simple incorrect specification and then validate it against the implementation, see where it goes wrong, and then gradually refine the specification until you get something that you're happy with. So it let us understand what we meant by correctness, which was very helpful. And it revealed a potentially serious bug that it would have been impossible, I think, to find this with conventional testing, just because it's quite a specific case. We have to take down some nodes and then bring them up and bring down the other nodes in a specific order that you wouldn't really think of doing if you're writing tests by hand. And another thing was that once we found this and the Basho guys sat down to fix it, they had this nice property that they could verify the new implementations against, which I believe was quite helpful. So the good news is Riak is eventually consistent, as far as we know, thanks to QuickCheck. Thank you.